matrix elements on the fly, cache ready, and in parallel. My name is Oliver. I'm a third-year doctoral student in the computational science department, and I use computational science to study the structure and properties of atomic nuclei to the center of atoms. So one reason to care about nuclear physics is the detection of dark matter. Dark matter is this mysterious substance which no one has actually ever seen, but we know is there because when we count up all the visible matter in galaxies, it doesn't add up to the total mass that we can extrapolate from the gravitational effects of the galaxies. One effort to directly detect these dark matter particles is with the LZ detector, which is a big detector buried under some mountains in North Dakota. What does this have to do with nuclear physics? Well, at the center of this detector is a big vat of liquid xenon. Now, xenon is a nucleus with about 130 nucleons. And what this detector is doing is waiting for one of these dark matter particles to come in, to strike the nucleus, and to kick it into one of its excited states. If this were to happen, it would emit some radiation, which would be picked up by the detector and turned into a signal. Well, in order to interpret these signals, if we were to see one, we need to have a detailed understanding of the structure and properties of the atomic nucleus and the excited states that it can reach. To find these, we need to solve the Schrodinger equation, which is kind of fancy, but it's really just a matrix eigenvalue problem, which are familiar to most people in computational science. The problem is that these matrix eigenvalue problems that we need to solve can be really, really large. So for example, certain isotopes of xenon would require a matrix with dimension 900 million, which would require a couple billion gigabytes of memory, which is something that we don't have. Fortunately, we can avoid storing the entire matrix by using a couple of techniques, one of which are iterative methods, which allow us to solve the extremal eigenvalues of the system, which are all we really need to understand the physics. So iterative methods go like the following. We start with some guess for the solution U, and then we apply the matrix H, and then we continually apply it iteratively until our solution, our vectors converge to the solutions. I have a code that I finished writing about last year, which does this and also uses some physics approximations to make it even smaller. And what I was doing before I started the current project was to generate this Hamiltonian matrix H, store it in memory, and then use it to carry out these K iterations to carry out K matrix vector products. But if we look carefully, the solutions that we get are actually these vectors H times U. And what this means is that in principle, all we need to store in memory is the vector H times U. So by taking advantage of this fact, I was able to adapt my code and only calculate the matrix elements of H as they're needed on the fly for each of these iterations. By doing this, I was able to significantly decrease the memory usage of my code. Basically, I went from memory order dimension squared to memory order a constant times the dimension, where K is the number of iterations, which is usually much, much smaller than the dimension. This is great because I significantly reduce the amount of memory that my program requires, but it comes with a drawback, which is since we only compute H as its matrix elements as they're needed for this matrix vector product, and we don't keep it around, we have to recompute it for each iteration that we do. So to combat the cost, this additional cost of using this on-the-fly algorithm, I implemented another algorithm called the Bloch-Lanczos. And the idea here is that we can amortize the cost of recomputing H by reusing it as many times as possible. And the way we do this is that instead of using just one initial guess for the eigensolutions, we use Q initial guesses, and at each iteration, we apply H to each of these guesses. This does two things. It allows us to reuse H multiple times, which has implications for cache efficiency. And it also tends to decrease the number of iterations that we need to do overall. Like I said, this is called Bloch-Lanczos. So I implemented this into my program as well. I also implemented a couple other techniques like pre-computing data that's frequently used, so I don't have to waste cycles on that. I flattened some arrays, and I organized them to increase cache efficiency further. So I did some benchmark case tests to see how this improved my program overall. So let's look at this example that I'm highlighting here with a dimension of 50,000. Before I implemented these changes, my program would have used 11 gigabytes of memory and about 4,000 seconds to compute. And after implementing on-the-fly algorithm, I see a huge decrease in memory, but of course it takes longer because we have to recompute each iteration. But after subsequently implementing Bloch-Lanczos, we do see an increase in the memory requirements, but now the total compute time was dropped by about a third from the on-the-fly algorithm. So by implementing these methods, I've used my computational science to increase the ability of my physics models to capture the relevant physics.